Okay, welcome back, everybody. So this lesson is going to be quite different. The focus of this lesson is backpropagation, and I really want you guys to actually understand at a concrete level of detail, down to the number, what's happening when you're training a neural network. And so I hope everybody was able to find the worksheet.pdf in the folder and either print it or get it ready in Adobe or whatever you want to be able to edit it and work on it during our lesson. But before we do that, we're going to have a short presentation, and this one's should be quite shorter than some of our other ones because a decent amount of it's going to be review. We're going to watch another excerpt of 3 Blue, 1 Brown because he just does everything better than I could possibly imagine doing it when it comes to visualization and explanation. But yeah, so neural network training by hand, that's essentially what the focus of today's presentation is. So just as a bit of a recap of what we learned last lesson, we learned what the architecture of a neural network is and how we pass information through it. What's exactly happening to each neuron as you're passing, an input example through a neural network. So just to recap that, right, the very first thing you want to do is you want to standardize your input before you input it into the first layer of your network. So in this example, you see what we're trying to do is we're trying to take different features of a house, such as the number of bedrooms or the square footage, or something to do with the neighborhood, some sort of ID, using all this information and mapping it to a final price estimate. So, so first of all, could someone answer real quick, is this a regression or a classification problem?
It's a regression problem.
Sure, yeah. And what makes you think that?
You're trying to predict a continuous variable, which is the final price.
Yeah, exactly. And for that reason, it's a regression problem. And like you could make the argument that like, oh, well, there's a certain granularity to what the price could be. Like it could be a classification problem with like a bunch of classes, but no, I mean like there's so many options that we just call it a regression problem. So yeah, it's a regression. So we standardize the input all the time before we feed it into the network. And before we even do that, the network has to have some sort of values for all the weights between different neurons. So we usually just randomly initialize those. Literally, it'll usually just be like a normal distribution between like -1 and 1 or 0 to 1, depending on your activation function. It's just straight up randomly initialized. And then we do a forward pass where we, pass in a certain example. And as you guys remember, a neuron is just doing linear regression, but with multiple terms, which is the weights from each previous neuron, and then finally adding some sort of non-linearity to it. And there's another slide that's going to show that in more detail. And the focus of today is backpropagation, which is when we get that final price estimate, and then we look at the real answer. What was the actual price of this house? Look at the difference between our guessed answer and the actual answer, and then start distributing the blame to each neuron in the final layer, or the second to last layer, to start seeing how can we change the weights to get a better guess next time. So this is the slide that I was talking about. It kind of shows more in depth another recap of what the neuron is doing. Like I said, it's just a sum of mx plus b's, but we use the letter w to remind us that they're weights of a neuron. So it's just a sum of wx's and then a final b term at the end. And all those w's, as you can see from the arrows here, that's just all the previous layers neurons that point to it and multiplied by their activations. And then finally, you do some sort of nonlinearity. That's the F here, sigmoid or ReLU. And as for sigmoid and ReLU, this is just a quick recap of what they look like. So sigmoid squishes the entire real number line. This is function notation. Some of you guys should be familiar with this, but if you're not, like the name of the functions on the left and then the colon just says this function maps from this space, and then the arrow says from this space to this space. So we are mapping the entire number line, the real number line, onto the range 0 to 1 inclusive. The square brackets means inclusive, meaning 0 is included and 1 is included. If it were round parentheses, then it would be exclusive, like do not include those endpoints. So yeah, sigmoid squishes everything just like this, and x equals 0, 0 gives you exactly 0.5 in the middle. And then ReLU is not a squishy function. So sigmoid is squishy. It squishes the entire real number line. ReLU just simply gives you the max of 0 and z. And the reason that it's become really popular recently is that it's just super, super easy to compute the derivative, right? I mean, in this entire section, you basically just know if the input is negative or 0, then the derivative is 0. Otherwise, it's 1. So super duper easy. But yeah, the downside is that it is not squishy. So next, to measure the loss or how wrong your guess is, in the case of binary classification, we use binary cross entropy. And this is also, you'll also hear this be called negative log likelihood, which is a more kind of mathematically descriptive term for what it's actually doing. Because if you guys have seen the equation, it's literally just taking the log of the probability that you guessed. So I mean, the output of a binary classification problem would be the probability that it is 1, and that's your guessed probability. So you just take the log of that and the negative of that, and that's literally it. And you see the benefit of this is that you exponentially penalize wrong answers. So this is showing if the true answer was 1 and you guessed that it was 0 with a, that it was 1 with a super, super low probability, the lower the probability, the more that you're going to be penalized for it. So that's binary cross entropy. And so then the whole magic of backpropagation is, like I said, using the chain rule of calculus to calculate the effect of each neuron on the loss function. If we nudged the weight just a little bit or the bias just a little bit, how would that affect the cost function? So we calculate the error and basically work our way backwards and find the loss for each neuron. And that's all gradient descent is doing. So we're going to see a little snippet of 3 Blue 1 Brown now, and he has a really good animation of this. Let me make sure my audio is working as well.
Let's just start off with an extremely simple network, one where each layer has a single neuron in it. So this particular network is determined by 3 weights and 3 biases, and our goal is to understand how sensitive the cost function is to these variables. That way we know which adjustments to those terms is going to cause the most efficient decrease to the cost function. And we're just going to focus on the connection between the last 2 neurons. Let's label the activation of that last neuron with a superscript L, indicating which layer it's in. So the activation of the previous neuron is a L-1. These are not exponents, they're just a way of indexing what we're talking about, since I want to save subscripts for different indices later on. Now let's say that the value we want this last activation to be for a given training example is y. For example, y might be 0 or 1. So the cost of this simple network for a single training example is AL minus y squared. We'll denote the cost of that one training example as C0. As a reminder, this last activation is determined by a weight, which I'm going to call WL, times the previous neuron's activation, plus some bias, which I'll call BL. And then you pump that through some special nonlinear function like the sigmoid or a ReLU. It's actually going to make things easier for us if we give a special name to this weighted sum, like Z, with the same superscript as the relevant activations. So this is a lot of terms, and a way that you might conceptualize it is that the weight, the previous action, and the bias all together are used to compute Z, which in turn lets us compute A, which finally, along with the constant Y, lets us compute the cost. And of course, AL-1 is influenced by its own weight and bias and such. But we're not going to focus on that right now. Now, all of these are just numbers, right? And it can be nice to think of each one as having its own little number line. Our first goal is to understand how sensitive the cost function is to small changes in our weight, WL. Or phrased differently, what is the derivative of C with respect to WL? When you see this del W term, think of it as meaning some tiny nudge to W, like a change by 0.01. And think of this del C term as meaning whatever the resulting nudge to the cost is. What we want is their ratio. Conceptually, this tiny nudge to WL causes some nudge to ZL, which in turn causes some nudge to AL, which directly influences the cost. So we break things up by first looking at the ratio of a tiny change to ZL to this tiny change W. That is the derivative of ZL with respect to WL. Likewise, you then consider the ratio of the change to AL to the tiny change in ZL that caused it, as well as the ratio between the final nudge to C and this intermediate nudge to AL. This right here is the chain rule, where multiplying together these three ratios gives us the sensitivity of C to small changes in WL.
All right, so there was a lot going on in that last slide, a lot of figures and subscripts and number lines and everything, but hopefully the animation part of the nudges, like that's really the key part that you need to understand is like all we're trying to do at the end of the day is see how nudging a weight affects the overall cost. And we just want to nudge them so that the cost goes down. That's literally all backpropagation is. So I highly recommend that you watch the rest of that video. That was just a small excerpt, but yeah. Let's continue. So just to sort of go over, you know, what we're sort of traversing here, if you will, you could think of like this terrain that we're exploring or traversing as a lost surface. So let's say you had a super simple, you know, parameter, just two parameters, two weights, and then the cost function was the z-axis. Then you could think of it as some sort of hill. And the derivative is telling you, the gradient is telling you which direction would you step in to increase your height, increase your cost the most, and you just go in the opposite direction. So yeah, that's what the negative of the gradient is doing, and the objective is to find the global minimum. But you know, you don't know that you're at a global minimum. It's kind of like you're zoomed in. You can't see the entire terrain. You can only see like what's immediately surrounding you and take small steps and just hope that you'll find the global minimum. But I mean, you could definitely get stuck at what's called a local minimum. So, so yeah, just a one final like review, I guess. You know, you standardize your inputs. You always want to standardize them. And can someone remind me, why do we standardize the inputs? What's the point of that again? Why not just put them in raw? And you can put it in the chat as well if you're unsure, or just make a guess.
Well, if you think about like images, like a huge image, if you're like trying to predict something with a lot of pixels, the network might see that versus like a small image, like 64 by 64. And it would weight those differently just because of the sheer amount of pixels in the bigger image.
Yeah, I see what you're saying. I see what you're saying, but usually when we have like a network for images, it just has to be the same resolution for all of them. And if it's not, then we have to resize them. So yeah, you're totally right. If there was some sort of like, if you had a network that, let's say, had like a maximum resolution and you could feed in small images, but then a bunch of the neurons would be zero, like, yeah, you're absolutely correct. But in practice, what we usually do is just we say, okay, every single image that enters this network is going to be this certain size. And if it's not, we'll make sure that's the case. But like another example, I guess a good example would be this one, right? So, you know, the final price estimate. So, you know, if you have 3 bedrooms and then you have 2,000 square feet, remember what the neuron is actually doing, right? It's just pumping those numbers through, you know, like WX plus B and then some nonlinearity. So obviously like 2000 is going to have like a way higher chance of activating that neuron, and that neuron's going to fire way stronger and more often, or yeah, basically just stronger than the one that just has 3 or just the one that just has 1. So we want to make sure that every feature is being weighted the same. We start off with this assumption that every feature should just be on a level playing field. It's really asking the question, like, for this particular feature example, you know, how much is the value for this, you know, for bedrooms? Does it have more bedrooms than the average or less bedrooms by the average? And by how many standard deviations? That's basically what it's asking. Rather than just saying how many bedrooms are there, because I mean, we don't really get a sense of, okay, is 3 bedrooms a lot as per this data set, or is it a little? Like, I don't really know. Is 2,000 square feet a lot? Maybe it's the smallest house in the entire data set. If that were the case, then it would be like a negative number. The standardization would be a negative number because it's less than the average. So yeah, standardization is really important because we want all the features to be on the same level. We want the neurons to activate based on the features, not just like the raw number. So that's why we activate them. And yeah, Megan, you said different units. That's a big part of it. Absolutely, that's a big part of it. Different units, like what does 2000 mean compared to 3? So pretty much, yeah, you're right. And it's easier to tell feature differences when they are standardized. Yeah, like comparison. It just comes down to comparison. So we standardize the input before we pass it in. Then we randomly initialize the weights. That's just the, like, we only do that once, right? Obviously, we only do that at the very, very beginning when we're initializing the network. And then let me go back to that final slide. Yeah, we initialize it once, and then we just repeat this, pass in an example through forward pass. You just pass in an example, backpropagate the error, and tweak the weights, and just keep doing that. Keep repeating that again and again and again. And remember last time we talked about stochastic gradient descent, which is kind of different because we're not just passing one example every time, we're actually passing a batch of examples. And all that really means is instead of just doing it for one, we like take the average. We just take the average of whatever batch size. And it just is like a little more computationally efficient because it's kind of more like you're taking like 100, let's say your batch size is 100. It's just like taking 100 examples from your data set and saying, okay, let me just pass in like the average of these 100 as an example and just update it that way. So that's the difference between stochastic gradient descent and true vanilla gradient descent. But yeah, you just keep repeating those steps and then you eventually converge. And that's all there is. So like I said, this was going to be, quite a short presentation. A decent amount of this was reviewed from the last time. And, a lot of high level talking about, nudges and chain rule and partial derivatives. But now it's time to like actually see, number crunching, what this means, what this actually leads to. And so we're gonna work on that worksheet. Hopefully, guys, you have that ready. It looks like this. This was written by Tyler Labonte, and he's a G. He did a really good job on this worksheet. And basically, I guess I won't have to explain it too much because he does a really good job of like, defining the problems. But you'll like sketch out a neural network here, and then you'll basically, he even gives you the answers, right? He says like, show that a standardized input is this value, and you just do the math like x minus mu divided by standard deviation. And just to remind you, look up here. This is the problem right here. So you want to remember these, like x1 equals 6. These are the specific examples that we're going to be using. But yeah, I hope that this presentation was useful to you guys, and we can take a little break now as you guys start to make your way into your small groups. But yeah.